what we heard about with Jan was that he was basically starting with some sort of neural network that already existed. He had a topology, he had the weights and the biases, and then he's changing them slightly so that this neural network performs in the way that he wants it to perform. So I've already skipped quite a number of my slides because he did a brilliant job of explaining quite a lot of this. And I'll just basically explain the work that is different because it's after he moved on to start his independent group. Okay, so the fundamental question that we are asking ourselves is basically, can we solve inverse problems over already trained neural networks? So the training problem is typically written in machine learning as I have a whole bunch of inputs and I want to predict the output. Then if we are to be using this model, sometimes what we might want to do is we might want to solve an inverse problem. We might want to ask ourselves, what is an input that achieves the desired output? So I've been on sort of an adventure in the last few years of sort of looking at quite a number of these problems, because one question that I have had for myself relatively consistently is this a real problem, right? Like it's a fun problem to solve from a mathematical point of view, but just because it's fun to look at from a mathematical point of view doesn't mean that it's always the right thing to do from just from a computational point of view. So one of the applications that we have looked at, and just as an example of the kind of thing that we're thinking about, is with this construction startup. So what happened with this construction startup is that they are managing these enormous construction projects. And I mean enormous on the scale of UK government is building a new high-speed rail from Birmingham to London, large scale. And what they do is they take a whole bunch of different indicators, and they predict how long it's going to take before some task gets completed. Then what happens, and the question that they want to ask themselves, is how do we predict how to make the duration of the task shorter? What are the things that we need to change such that the duration of the task is going to be different? Basically, can we find a combination of the tasks that reduce the time span? Now, here where we can possibly be useful is basically that there are possibly other constraints in the problem that constrain us somehow in terms of the left-hand side. Where we are possibly less useful, and here's the trade-off that we have with the company, is that oftentimes our optimization just ends up showing us maybe the trained model is less good. It's basically an adversarial type generator, right? Another example that we've been looking at, this is the sort of my naive version. We have a more complex version that is with some actual finance professors. Was one of the things that happens is, I'm middle-aged. Like many middle-aged people, I go into large amounts of debt to own a very small piece of property. And the way they decide whether or not I can borrow this very large amount of money is based on my salary, my age, my credit history, all sorts of information. And then it says whether or not I can get this very large mortgage. And one thing, well, the way we pitched to the finance professors, and they were basically like, you are so naive. But the way I pitched this to the finance professors originally is, well, maybe I'm initially denied some sort of mortgage, but I want to know what are the differences before I would be approved. This would be the kind of problem that I know how to solve with optimization. And they told me, you're an absolute idiot, because basically that's not the kind of data that a company is ever going to make available to users. But what they did instead is they proposed a much better version of this, which we're still under some development, so I'm not presenting the full version, but that basically we look at, we are able to analyze what is happening with these different credit factors when looking at different groups in a population. Another example that we have been looking at, and this is actually work of Shicheng, who's sitting here. So a lot of this work is that I'm presenting today is by Shicheng. So the way to know how this presentation is going is that if he starts hiding under the desk, you know I'm getting it wrong. So basically what happens is that at BASF, and we have Bruno and Inka here who are our employees there, what they would like to do sometimes in some applications is take molecules and guess at physical properties. Now, maybe if you wish to design new molecules, maybe you wish to go from physical properties back to a molecular representation. Now, this, I could think of my forward path as a prediction. If I have some model that then I want to make decisions based off of my model, I might wish to go backwards. Okay, so these are just some examples. And what I want to mention is that we have an open source toolkit that we're quite excited about. I had skipped several slides because Jan nicely covered an awful lot of the very intro slides, but I should acknowledge that there are quite a number of tools that are somehow similar to this, solving exactly the neural network verification problem, which Jan covered at the beginning of his talk, are these codes. These codes at the bottom, these are more similar to OMLT, which is ours, and I realized that I had missed one, so Mark Turner, who oh, there he is, hi. I didn't recognize you. So Mark Turner has his by skip opt-ML, right, which is similar in ideas to what I'm going to be presenting here. So I apologize, I didn't update this particular slide since December of last year. So ours, which is similar to what others do, is basically that we are going from an already trained surrogate model. We take this as a sort of a rule that exists, and we turn this into PyOML code. Now, this is basically just a glorified translator, right? Because all that we're doing is we're taking a surrogate model and we are representing it using optimization constraints. And we want to ask ourselves when and where is this useful? So Jan mentioned these verification examples. Then where we really find ourselves the most useful is in engineering applications. And the reason is that in a lot of engineering applications, or at least the ones that I'm familiar with because I'm a chemical engineer, we end up having some big optimization problem where we know an awful lot of the constraints. So we know that on a reactor, flow in is equal to flow out, or we know that we know what the costs of things are, or we know we have to schedule some unit. But then because we're chemical engineers, we also have some reactor somewhere where we don't maybe really know what's going on inside. And so instead of trying to have some poor researcher sit down for 4 years and figure out what the underlying PDE is, maybe we wish to represent how this reactor exists as a model trained from data. And the reason that we find this to be the most useful is that ultimately, if we are just going to be sort of optimizing over a neural network in the sense that, I have some understanding of what are good properties that I want to get out of my molecule, it might actually, in a particular situation like this, be more useful if I was actually just to use some sort of heuristic, some sort of genetic algorithm to just generate an awful lot of possible inputs and then get the outputs, right? So basically, where our tool is going to be useful and where these tools are useful in general is when there are an awful lot of constraints to the problem, when there's an awful lot going on. Okay, nobody's asking any questions, and I do punish no questions with just continuing to drone on and on until lunch. All right, you want the punishment of droning on until lunch? I can do that. All right, so basically this is a lot of blah blah on applications, but the reason that I think that that's useful to talk about is that I want to go to specifically the type of optimization that we're trying to solve with our software, because I know that I'm talking to an awful lot of very talented researchers, and I always try to convince people to do research in areas that I'm interested in. And so what I want to show you is less how we've answered everything, but more how there's tons of stuff to be done. And if you're interested, it sure would be cool if people would look at this. Okay, so the kind of problem I'm interested to solve, the top bit looks super familiar to us from any kind of optimization anything. I want to minimize some function subject to a bunch of other functions. The only reason I'm doing f there is I want my f to be something that I can write down. Maybe this is semi-algebraic. Maybe these are just linear constraints. I don't know what. And then I want additional constraints. I want these additional constraints to be something like obey this neural network as a constraint. And so what my x's and y's are in this problem is that my x's are the input to my surrogate model, my y's are my outputs from my surrogate model, and then somehow my surrogate model is itself a constraint. The reason that I find this way of doing things useful, and the reason that I think we've been quite successful with our OMLT tool, is that if we can just abstract away this entire neural network for a user, it just makes it a lot easier on, say, an engineer that doesn't feel like coding up the constraints that Jan was mentioning just now. You don't have to have figured out all of the big M's, and you don't have to consider the different formulations yourself. So we're using this technology of a Pyomo block, and then we are allowing the Pyomo block to encapsulate a lot of different items. There we go. Okay. So basically, this is what I wish you would do for me, is that we've talked about these optimization problems. You embed a already trained surrogate model into an optimization problem. And then these optimization problems get difficult to solve. They're relevant from an actually being sort of useful to society sort of application, as far as I can tell, when there are constraints that make the entire optimization problem difficult to solve. Otherwise, typically what you would do is you would just maybe use some sort of heuristic to evaluate the surrogate model in a lot of different places. Why these can be very, very difficult to deal with is, first off, you end up with non-convexity. For instance, when you're dealing with neural networks in the activation functions, when you're dealing with trees, when you have the splits. You end up with, if you have some sort of graph structure, for instance, when you have a graph neural net, you're turning on and off an adjacency matrix. There's non-convexity that arises there. And then these get to be very large problems very quickly. You might end up with these non-convexities at every single node, for instance, in your neural network, or maybe even at every edge. So my presentation is specific to OMLT because I'm selfish and that's what I work on. And what we are currently doing with OMLT is that it's built right up against Pyomo, where basically from the very beginning, anytime we introduce a variable or a constraint within OMLT, we are introducing a Pyomo constraint, a Pyomo variable. We have a pull request as of a couple months ago that allows us to have a backend to other algebraic modeling languages. Right now, we have draft connections to JUMP and also to GAMSPy. So this is in progress, although we need some help. And then if you are interested, there's an awful lot of algorithms and models to be developed. So there are these things called skip connections for neural networks that we do not have in OMLT. We do not have anything to do with recurrent neural networks in OMLT, just because these are super difficult problems to solve. And then we have all sorts of algorithms wish lists. Okay. So you want me to take an example and say why I think recurrent neural networks would be useful. I think recurrent neural networks could be useful for some chemical engineering style scheduling problems, where you are forever having some sort of time series like update. That's where I would put them. I would say get in touch with, I mean, I would, look, I totally agree with you, Mark. These things are not useful unless you have an application, right? Because one of the things that's key about this, and something that I have definitely found in everything I do related to this, is that there's a lot of made up problems that are not useful. And there are also a lot of problems that are useful. We are still doing more than 10,000 downloads per month on OMLT. We're quite sure that it's being used. I get it, downloads are like Facebook friends and they're not real. Yeah. But for me, it was almost like we were getting so many downloads, and then it was this step back of, okay, where are we useful? For me, where I understand that we are useful is in engineering, basically where you understand most of what's going on, and then you have something you have learned from data. And then we've been working a lot with these finance professors, and we seem to have something there. So basically they have an awful lot of rules related to whatever fiduciary responsibilities. They make it sound better than I, but yeah. Yes. Correct. Actually, that's a good point. That's a good point. So something that, I mean, if it should be a PDE, maybe it should be a PDE, right? That's why I didn't want to, I mean, even, I know people who can optimize over PDEs, right? But definitely something that is somehow a little bit dynamic is what I would be thinking about. Good. Yes. Okay. So I was asked about non-convex activation functions. I want to mention what I mean by that and how I think you all can help. Is that reasonable? Okay. So Jan talked about this ReLU activation function. It's either 0 or it's slanty. And he dove into a big M formulation in some detail. He also developed this partition formulation, which is basically in competition with this big M formulation. Sometimes one is better, sometimes another is better. At about the same time, this is Sven Leifer, and he basically said, hey, wait a minute, either you have 0 or you have a slanty bit. I know how to formulate that using nonlinear optimization, and that's what Sven did. So here what I mean by non-convex is that basically you have this hinge where basically you're either 0 or you're on the slanty bit. So those are 3 possible formulations, which is the best. That's context specific. Are there more? It would be cool if there were. Also, you could think about sort of combining nodes or something like this. Then for the non-linear activation functions, at least in OMLT, what we have is we have a number of them that are somehow monotonically increasing. So we can OMLT came because the group of Carl Laird, he developed IPOpt, and myself talked to one another, and we realized we were working on exactly the same thing, and decided not to play I have the best open source translator of machine learning everything. And so basically we have good nonlinear optimization because of Carl's team. And so we take quite a number of sort of nonlinear activation functions that we are translating. And to the question of how we are representing them, we are just kind of throwing them to Pyomo and letting somebody handle it. Ask again. Yes. That's non-convex, right? Well, okay. It works in the sense that that OMLT can take it from a standard library. We have good input, and we can translate it into Pyomo constraints. That Pyomo constraint is going to involve a TANH, and then we say, God help you, you go and solve it. Okay? Now, this is actually one of the reasons that I bring a presentation like this to a place where I know that there are a lot of expert optimizers and people who are sort of training to be expert optimizers, because the challenge, as far as I'm concerned, is you deal with it. You know that it makes it more expressive, right? You know that it makes the neural network nice. I can write it down in mathematics. That's the only thing I'm saying I've done. How are you going to deal with it? I don't know, you do it. The ways that have been tried so far is that, and we have both of the ways that we know of that have been tried so far, is that one thing we can do in nonlinear optimization, if things are getting complicated, every time we get some sort of expression that we say, hey, that's a little bit too complicated, I don't want to deal with it. I could, every time I see a TANH, for instance, I could just say, I'm going to make myself a new auxiliary variable. And I could basically have the number of auxiliary variables get very, very large. This might be nice from an optimization point of view for anything that would try to exploit sparsity when trying to solve. So a lot of the nonlinear optimization solvers are going to like things like this. Another thing that you might want to do, and this is the paper with Artur Schweitman and Alexander Mitsos, and they were actually exactly looking at this TANH activation function, is you might say, well, that's awfully confusing for a solver if every single time I introduce a TANH function, I'm making myself a new auxiliary variable. Actually, that was a problem that always was in a relatively small input space, because you could only choose your inputs to your neural network, for instance. And it's not like every node in the neural network has to be represented as a variable. So what you could do instead is just make your expressions more and more complicated, and that's what they like to do. So OMLT will give you both of them, but then how you handle them algorithmically, that is what I'm trying to say is not solved. So thank you for the question. I think I saw another hand, yeah. Okay, so this is a good question in terms of asking where we sit. We assume we've been handed the neural network from on high, like it's been given to us. We must work with the one that we are given. We do not intersect with the training process. There are some neighboring papers, most notably probably this optical, Maragano et al. What they're thinking about is sort of doing some sort of training process as well. So they'll develop slightly different models. More questions? Yes. What are the gains? The gain is that I'm holding on by my fingernails trying to support an open source project that is I mean, look, it's going great, right? We're actually getting used. But if I can get the GAMS guys to connect to it, then I've got a lot of help. And because, well, I mean, I'm not trying to, exploit anything. I just wish to make it relevant in a way that is beyond Pyomo. Basically, give it more life. And in particular, if I can get companies involved, that's amazing. Other questions? Okay, yeah. There is a lot of work that is concurrent with ours that thinks about exactly that. some of it, I mean, it's a really interesting line, and I've been asking myself how and if I can get into it, right? Because there's a funny trade-off. What OMLT will do is it'll take the viewpoint that you give me the neural network and then God help you when it comes to solving it. That's Pyomo's problem. You deal with it, which is maybe not always the right thing to do or the best thing to do. Where I haven't figured out what to do or how to do it is how to balance. I know that neural network is too big versus not wanting to be too prescriptive in terms of making a decision to change the neural network in a way that maybe a user didn't want. So I haven't squared that circle. If you have ideas, I'd love to hear. Yeah. Okay. Okay. So Jan already showed basically a big M formulation where you have the inputs coming in. You can tell we're collaborators because we have a very similar graphic. You have these inputs coming in, and then you have outputs. I can encode this using, for instance, Big M or other technologies as I may wish. A thing that this is Christopher Hajoni, who's sort of friend of Skip and also Shicheng in the lead. One of the things that can be fun to look at is what if I now have a graph neural network. What's going to happen in a graph neural network is we're going to have layers where instead of sort of maybe being independent of one another as they were in the previous in the feed-forward neural networks, they're now connected to each other somehow. And what's cool is special structure in these things is that the graph repeats at each layer. So if you know the graph at one layer, you know the graph at the other layers as well. Okay, so we still, in this case, I'm going to put a ReLU activation function. The reason that we only studied ReLU activation functions is that we wanted to ultimately be solving a MIP. I'll show you why in a minute. And then what we end up with, if I already know the structure, for each one of the nodes, and so let's focus on x0, for instance, I take x0 times some weight that has already been trained. So this is my variable x, and my weight is a constant at this point. And then I also need to be paying attention to each of the nodes here, x1, x2, x3, and x5, that are connected to x0, so everybody that has an edge between them. And then in the simplest sort of message passing neural network framework, what I end up with is that I have my variables times these weights. The variables are the ones that are the features that are attached to each of the nodes that are adjacent, and then the weights are pre-trained. And then I have my biases, and then I have my ReLU. So this is a fixed graph structure. If I have a fixed graph structure, then what I can do is that I can go back to basically the problem that we were looking at with Jan, where we are just looking at individual ReLU functions, and all I have to do is mind my P's and Q's, and it's the exact same problem as before. Where this gets fun is if I don't know the graph structure. So if I don't know what is going to be connected to what, then I end up with an awful lot of fun integer programming to do, where basically I have weights that I know, but then whether or not there is an adjacency is a question mark. Anyway, no, look, basically, I mean, the challenge I have is the same challenge that Ambros and Thorsten live, right? Is that basically I'm trying to get funding for software maintenance and development, which is very difficult, right? is I can very easily write myself a research grant that says I'm the first one to do something. And I bet I could even convince reviewer number 2, if he was you, that a recurrent neural network would be something I would like to do. And I have a good reason, I have a good application, right? But hey, Python updated and now my backend is broken is not something that the research councils will pay for, right? And so that's where I end up clinging on. So basically, there's the stuff that is easy. There's the stuff that's easy to do, which is the new stuff. Or not easy. I mean, it's tough from a mathematical point of view, but I'm sitting and writing the grants, right? So there's the stuff that I can easily write, and then there's the stuff that is going to keep our project afloat, and these are different things. And so basically, we're just trying to diversify past anyone can get a new job or have a kid, and we still are able to do our maintenance and development. Okay, it really is lunchtime.